Okay, everyone, I guess we're back for the last bit of our tutorial section. Chris Kalos, one of our team members, is going to talk about how to create a new planet. And after that, we'll have a 15-minute break or so, and then we'll have a final Q&A, everybody. So Chris, do you want to take it away, or should I show the remaining slides, or what do you want to do?
In progress.
Assuming you hear me.
Yep. Yeah. Can you hear me?
We don't hear you very well.
Okay, is that better?
Much better. Thank you.
Okay. Just going through my headphones. All right, here we go. All right. You can see, so I'm going to be kind of doing a terminal tutorial. All right, so this is just going to be sort of combining, I wasn't here yesterday, but combining a little bit of things that everyone has talked about, presumably, and actually just going through a run deck. This is going to be based on one of Mike's old run decks, changed it up a little bit just to make it tutorial friendly. And then, yeah, we'll kind of go through line by line and say a few words about everything. This is an old Proxima Centauri run, so, but things are going to be, I'll show you how to modify everything based on your desired planet and talk about what we can provide if you want to start simulations tomorrow on your sort of favorite hypothetical exoplanet, things that we can already provide input files on and guidance on, and things that might involve more labor on your part. Luckily, we've done a lot of stuff so far in terms of the whole group, so a lot of options are already sort of, you could just email us and I'll give you everything you need and you could change a few numbers around. But all right, we'll talk about this. And all right, so, and if you haven't seen so far, I put in the chat the folder where you can kind of just get some of the input files if you don't have everything already, and this run deck. So I use Emacs. I'll just.
Could you make the fonts a little bigger?
Okay. Can I just make the window bigger?
Don't make the window bigger, make the fonts bigger. So make your window back to the default size and then use Apple Plus.
Oh.
Make the fonts bigger.
Is that? Oh boy.
Make your window smaller before you increase the fonts, because your window.
Got it. Okay. It's doing it. I've never done this.
You're getting it. That's better. A little bit bigger, maybe. Not the window.
Yeah. Is that?
Hope everybody can see that a little better now. That looks good to me.
Okay. Thank you. All right. So at the top of the run deck, there's going to be space, and oh, by the way, this is in my decks directory. So I have this is on Discover, but I think when you download the model to your local machine, I haven't done that in a while, you'll have some different directories for input files and so forth, and you'll have a sort of area for your run deck. So whatever that directory is, you can create, put your .r file at the top. There's going to be just some, just write for your own sanity, the documentation of some things that you want to know about it if you go back 2 years later and look at the run. So the top here, I'll talk about this is for a dynamic ocean run. So some of these are specific to a dynamic ocean. I'm sure yesterday people talked about the different configurations. You could run Q-flux oceans if you want to prescribe the ocean heat transport, or fixed sea surface temperature runs, which aren't used frequently, but they can be used to prescribe the sea surface temperature as a boundary condition. But this is a dynamic ocean run deck, and that's going to be reflected. There's going to be a lot of these kind of modules and resolution specific kind of source code things that are at the very top of the run deck. Some of which usually you're not going to have to change any of this. They'll have to be changed if under some specific circumstances, or if you're doing a different version of the model, different resolution and so forth. But it's probably best to email us for any of these things. At the top, you're going to have maybe just one thing that will have to be changed is this planet params thing, and I have proxenb here. Now, I think I'm going to go to another directory, which I know people have talked about this model e/model/shared directory, and then you have planet params mod.f90 here. And if we go to that, I have populated a lot of this that you won't have necessarily, but I have this proxenb, which is going to require you to put some things about the planet, notably the gravity, the unit, that they have information about the units at the top of this file, but some of them are obvious. This is meters per second squared, and the radius of the planet in meters. You do have to tell it what the molecular weight of the air is, and I have a file which I can share if this hasn't been done already on kind of how to calculate everything if you're not sure. The surface pressure and the sort of the mixing ratios of things like N2, O2. You can often add some things like H2. Greenhouse gases like CO2 you're going to do elsewhere, so that is not done here, but you do have to take that into account in your molecular weight. All right, so once you put your and by the way, the default, it was mentioned, I think, by Tom earlier that you at least need something that's not, I don't want to say not Earth twice, not Earth, not space Earth, but we have this thing called not Earth, which is just a placeholder for any arbitrary planet that is different from Earth, because this just triggers your ability to change specific orbital parameters and so forth. If you don't have this in there, then a lot of things like obliquity, eccentricity, and so forth are going to default to Earth values. So you have to have some planet here and then make it consistent. All right, some of these things, for the default templates, well, we have templates usually for GIST radiation and for planet radiation. I think a lot of people here are going to be using Socrates as the default, and so that's what this run deck has. All right, so let's jump into things that you are going to be changing when you start a new run. And this is, okay, so we have all our initial condition files that have been talked about, AIC, OIC. So this is going to be your atmospheric and ocean and ground initial conditions and your topography. Now I have, let's see if I have the panoply open. Let me get rid of that. Yeah, my panoply window disappeared. I don't know how to. A lot of these most of the input files are straightforward, but this is probably going to be the most manual labor you do when you set up a new run. Now that said, so if we just go to your topography file, for example, you're going to see a lot of, for example, your fraction of ground. So you can see in this one, it's just Earth continents roughly. The format of it, so it's, you know, a lot of ones and zeros under these, and so it's pretty straightforward. We have already we have all the initial condition files you're going to need for a lot of standard simulations, such as Earth, continents, aquaplanets, land planets. So it's probably best to email us for these already if you're doing some, or Venus, Mars, and so forth. If you're doing some completely new planet with continents, with, you know, you might have to make a new files. But this is not too hard of a process once you get the hang of the format. And there does have to be some self-consistency in where you put land and where you put rivers and that kind of thing. But once you get the hang of this process, it's not too hard. I did comment out it should work if you want to use kind of these top, if you want to reproduce this run deck on your own time. This is for like aquaplanets. You'll have to change your directory where your input files are, and then this is for Earth continents with Mike's bathtub ocean, which, as he mentioned, is something we've kind of done to carve out the the continental shelves, which helps when you're doing colder than Earth simulations. The model tends to freeze to the bottom, which the bathtub avoids. It's kind of a hack. And in the current version of Planet 1.0, you put in river direction files if you have continents. I think in the new branch of Planet 2.0 and moving forward, this is going to be replaced by kind of topography-driven river flow and so forth. But right now, in this version of Planet 1.0, we put these files in here. I think some of these I don't want to go through right now, but we do put in some things for soil textures, and a lot of these are not used for like aquaplanets, for instance. And then I know Igor mentioned this vegetation file, which I actually have it pulled up here. So this is this standard vegetation file will just have things that you can prescribe for, and for most purposes, you're just going to be having bright soil and dark soil, unless you actually have vegetation, which you probably don't want for exoplanets. But the bright soil, these are just numbers that add up to 1. So here the bright soil is 0.5 or 0.4, I guess. And so the dark soil would be 0.6. And the surface albedo is a fraction weighted average of the albedos of these two things, and those albedos are written down somewhere. I think there's a source file. I think dark soil is 0 and bright soil is 0.5 or something like that. So if you want a surface albedo of 0.2, you would just change the fractions accordingly. Of course, when the model runs, when it rains over soil or snow deposits over soil, the albedo does change, but this is for like a sort of bare ground surface albedo that you want to start off with. And then GL melt is something we use for to put some, so this model does not have dynamic ice sheets, and so when we kind of cap the snow depth to something. I think the default is something like 2 meters, or someone can correct me, but we don't let snow just pile up infinitely at grid cells. And so if it does, we kind of just put it somewhere, and that GL melt file gives the masks for where to put that water if you have oceans. Okay. But again, for aquaplanets, a lot of these are not important too much. Okay. This stuff is not going to be changed in general. We have a greenhouse gas file. This is just a text file. If you open the file, it's very straightforward. It's just your CO2 and CH4 and a few other gases in the units are in those files. So it would just be a number like 300, or I guess in this case 376. And you would tell it what the mixing ratio is of the greenhouse gas. And actually, let me just skip down below just to add one wrinkle in that. And we do have these X multipliers like CO2X, CH4X. You do have to keep in mind that these multiply whatever you put in the GHG file. So if you have a greenhouse gas file that's say 100 ppm and you put CO2X equals 2, then your boundary condition is 200 ppm of CO2. So you just want to make sure you don't double. You can do it however you'd like, but some people just put 1s in here and then adjust the multiplier to whatever they want. Some people put these all to 1 and then put what they want for the greenhouse gases here. So just make sure you don't do double counting or anything like that. All right, this is O2. This is an oxygen-free atmosphere, so we put some things like O2x equals 0, and actually everything is 0 in here except for CO2. And I don't think there's a way to N2x, but this is a nitrogen and CO2 atmosphere. Okay, now we get into our star and spectrophiles, which Eric gave a tutorial on, and there's documentation on. I just will briefly guide you to the directories where these things are. So first, actually, there's a stellar spectra folder where you want to find your star, and these are currently available stars. And if you need a new star, then you probably email Eric, but we have a good list that is populated at some frequency for a lot of standard stars. We have the sun at different ages, we have Proxima, and a bunch of these other stars, and then these LTEs are sort of theoretical spectra for stars at different temperatures from 2600 to 4500. I don't think we have a hotter than solar star in here yet, but that could be put in at some point. And then we'll go to Spectrophiles, where, and this is where you have to read the documentation or talk to Eric just to find a spectrophile that is appropriate for your star-atmosphere combination. And it is the star-atmosphere combination that matters. If you have a dense CO2 atmosphere around the sun, or a Earth-like atmosphere around an M-dwarf or something like that, you want to take into account both of these things and find the appropriate long-wave and short-wave spectrophiles for your particular simulation. So you can find the options in these folders. But for more information on how to do this right, consult the documentation or Eric. The planet S0, so this is important. This is your total solar constant, or your stellar constant. So Earth is 1360. That's the amount of energy that's incident on a sort of perpendicular plane at the Sun-Earth distance. This is the prox B value. I think when Tom was talking, he also mentioned you could do this like mean distance parameter if you put that in there. We don't typically recommend, because you're just going to end up, this would be like 1 by default. If you did 2, it would reduce this value by a factor of 4 because it's an inverse square law. So it would be, 81 divided by 2 squared essentially if you did something like that. But I just you don't need to use it. Just decide what your solar constant is and put that value in there. Just keep in mind that it only changes the total stellar flux. There's no orbital dynamics going into this, so it doesn't change the orbital period. There's no Kepler's laws that are built into this or anything. So you have to change everything kind of manually, which I'll talk about the orbital period as we go down. This is not going to talk about mesodiffusivity right now. We have, just kind of from learning over the years of finding various crashes, we have various flags that we kind of adopt to avoid certain flags, such as minimum or maximum temperatures that are sort of Earth-centric. Things that we want to get around, we have this thing that helps with if you have different topographies, it adjusts your sort of atmosphere a little bit. We have various flags for your error in mass checking, and this R tau has to do with drag at the top of the atmosphere. So because it's very thin at the top of the atmosphere, you end up causing high winds or very fast temperature changes and so forth. So we had there's a little bit of I don't know much about this, but there's some stuff that people have done to avoid errors that result at the top couple model layers when you start running a simulation. And so we have some of these in the rundex to avoid those. All right, now on to some parameters that you're going to want to be. I don't want to use Siri. This planet name proxnb is the same as what we did up here. I think it's written down twice. I don't know why, but write it down twice. And all right, planet name equals proxen b. And again, if you don't do this, if this line did not exist, then everything below it would default to Earth values, and so you would not be doing the planet you think you are. So in this particular example, we set the eccentricity to 0. If you wanted 0.2, it would be 0.2, whatever the Fortran format is. And obliquity is in degrees, so 45. You just do whatever obliquity you'd like, and the orbital period is in seconds. This is a synchronously rotating planet, which means that the orbital and rotation period are equal, and so you just find whatever value you want, make them equal, and that is a synchronously rotating planet. If you want a spin orbit resonance, say a 3-2 planet, then the rotation period would be faster than the orbital period, so it would be a smaller rotation period by a factor of 2/3. You get the idea. Quantize year length. So Tom talked about this as, I think the default is true, but you do have to put this line in here. Otherwise, I believe you will crash at runtime or on compilation. And so I think the default is true. That forces an integer number of sidereal days into the year. I think I got that right. And so 365 into 1 year, for instance. This doesn't, for a 2-1 resonant planet, you can have this true or false. It would give the same answer. For a 3-2 spin orbit resonance, you can't have this to be true because obviously 2 doesn't go into 3 an integer number of times, so this has to be false. So it's just kind of a weird thing around these kind of synchronous, these planets where you have a rotation and orbital period of the same order of length. So just when we get to our kind of sanity checks at the end, I'll show, looking at the top of atmosphere stellar distribution, just to make sure you kind of have done this right. I think Tom also talked about there's an hour, I forget an hour angle offset you can do. We won't do this now, but it's, I think we've only done this under one particular condition, which I think some runs that Mike did or Tony Del Genio did, I forget, that place continents differently relative to the substellar point of a synchronously rotating planet. So if you want the sun, say, over the Pacific Ocean or the sun over Africa, instead of changing the topography file, you can just change where the sun goes with an hour angle offset parameter. But usually that's done.
ROCKE-3D paper, actually.
Okay, got it. All right, yeah. So that's, I think, probably the only time you need to use it, but as a default. And for aquaplanets, it doesn't matter because with aquaplanets, longitude doesn't matter. All right, we have some flags. Yeah, I think most of this stuff you will not be touching. Yeah, the stuff is not going to be touched in general, and if you do, you probably want to consult us. We do have some other time step related things which will come into play when you start a run, or if you encounter crashes, then your time steps will be something you want to look at first. I think the defaults are 450 for when you start a run with the 4x5 resolution model. The defaults are B450, and I think these DT and DT-XU filter and XV filter are the same, so you want to keep those the same. I reduced time steps for some runs to help with this numeric stability. Same with DT source. I think it's 1800 as a default. But these can be, and there's certain rules. I think it's an even, I think what's the rule for the, I think this needs, I think the 225 needs to go into DT source, something like an even integer number of times. So, but these are the defaults that you can use. And then NRAD is 5 by default, and it needs to be 5 or 1, I believe. I'm not sure if any other values are allowed. I don't know the reason for this. It has to do with how radiation is averaged over some length of time. Someone else can talk about that, but it needs to. So 5 is our default, but it's it can if for extreme climate scenarios, sometimes we'd make this 1 at the expense of a much longer computation time. Or for if you're interested in things like creating spectra or something like that, that might have to be 1. I'm not sure about these details. But
can I chime in on that? So
yes.
NRAD equals 5 because of Earth, where we have a 30-minute time step and the 24-hour day time, the duration of day. So if you can, every 5 time steps, which is what NRAD equals 5 says, means that you run the radiation every 2.5 hours. And that does not fit exactly in the 24 hours. And this is important, so you will get an uneven sampling of every other day, and then at the end, on the long run, you will be getting a mean sampling of radiation throughout, an even sampling of radiation throughout the day. So if you change the duration of your day on that planet, then you might need to revisit what value to get for NRAD. It must be a value that says number of time steps per day on that planet divided by NRAD should not give you an integer. That's the idea.
Okay, got it. All right, so that's, thank you, Costas, for that. If you stick with these time steps, I think you're okay without changing things. But if you need to start doing crazy things, then yeah, let us know, or Costas knows. All right, let me think. And then, all right, so down here, a lot of these are not going to be changed. Some of these things, so KRSF actually changes the frequency of RSF files, which are these restart files that you can pick up. If you have a run that crashes, for instance, you can pick it up off the last restart file, or if you want to start a new simulation with a different iStart, you can use an RSF file. But this value changes the frequency of restart file output, which these are large files, so you don't want to do it like every month, but you also, I think, so 120 does it once a decade. It's 12 times 10. So you get every 10 Januaries, I believe, is the frequency here. In this run deck, I have an nmon_av parameter, which changes your default output for post-processing. Right. So if you have, I'll show you an example of where this is useful. So if I go to my output, I've already run a few years of the simulation, and the default for the model is to produce output at the so-called the months. So you'd get a January and a February and a March and so forth. Now for these very short period planets, for an 11-day period, the output occurs it's every orbit times 12, right? So you would get essentially every 11 Earth days is 1 year of that planet, and so you would get output very, very rapidly, because you would get essentially you would just be loading up your disk space with output for an 11-day orbital period planet. You could change nmon_av to be 12, so instead of January, February, March, etc., you just get an annual file. Now this annual file is still 11 Earth days, so it's very short period output. So you could change nmon_av to be like 120 or something like that. So it's every 10 orbits or every 100 orbits and so forth. So that might be a more strategic option for very short period orbit planets. All right, let me go back. We are almost done with this part. Okay, and I think that's all I want to say about this part of the run deck. And we have the at the bottom here. So first of all, Igor talked about iStart, which is the default is 2, which starts your run from initial conditions. So if this is 2, then it picks up off of your, sorry, I'm scrolling, but it picks up from these initial conditions. So if you open the AIC and OIC file, you'll have information about the temperature and ocean salinity and pressure and so forth. iStart2 picks up from those initial conditions, and then you would run the model forward to an equilibrium. If you make other choices for iStart, 8 or 9, we talked about, then that picks up from an RSF file that you would provide in the AIC line. And then your year I, so this would start from, obviously years don't matter for exoplanet specific years, but for Earth runs, these choices can matter. But for exoplanets, start from year 1, January, and so forth. And then whatever your final year is, remember for short period planets, such as an 11-day orbital period, a year is, it's actually an orbit, it's not an Earth year. And so you are going to need a lot of orbits to come to equilibrium. And so this number, year E, should be pretty large. And I don't know, I don't know what the planet 1 versus planet conditions are. I think if you want to go to 5 digits on planet 1, you have to put another line of something. And I'm not sure if that's changed in planet 2 yet, but we can go up, we can go more than 4 digits. So you can, and that's going to be fine for any purpose within the constraints of what we do for ROCKE-3D, of course. So I think that is what I want to say about the run deck. Now, once we go to sorry, I want to just show. So we're gonna. I already have some output, as I mentioned. These are the restart files that are, as I mentioned, are accumulating every 10 orbits in my case. And then you get ACC files that are output by the model. So at this point, you can start doing post-processing and looking at your results. So I'm not sure, sorry, I wasn't here yesterday, so I don't know if scale ACC was discussed, but you just scale ACC your file and put, say, AIJ or AIJL or OIJ, whatever you want to look at. AIJ for the lat-long atmosphere, essentially. And so that will create the AIJ file that you can start looking at things like temperature and net radiation. You can use net CDF commands. I brought this over, I think I brought year 8 over to Panoply just to show you what some of this looks like. If you are looking at, say, your net radiation, there is a variable called net rad MS. You would put that file, and this would tell you the value. Right now, okay, so this is an 11-day orbital period, and we're only averaging over 1 year at the beginning of the simulation. So obviously, this is very far from equilibrium. We're 88 watts per square meter out of equilibrium. It's the third number is the global value. So you want to run this number, or you want to run the simulation long enough that your sort of time average net radiation is below 0.1 or 0.2 or something like that. So this run still has quite a while to go. And you do want to average over an appropriate window of time, such as an Earth decade or something like that. Okay, but once we get our AIJ file, we can start looking at a few things for sanity check. The one thing I pointed out was the incoming shortwave radiation at the top of the atmosphere, which is this INC SWTOA. And if you click on this, this will make a map. And in this case, we have a synchronously rotating planet, and we want to make sure it looks like a synchronously rotating planet, which it does if you if you have, say, an Earth-like pattern where it's a horizontal in latitude, latitude-dependent profile, then you've done something wrong. So make sure you do this at the beginning of your simulation once you've generated a year or two to make sure that your flux distribution and your magnitude is what you think it should be. You can look at T-surf, which is just surface temperature. This is going to look strange at first because what's happening here is this run is very far from equilibrium, and so the land, this particular simulation has Earth continents, and so the land has adjusted very rapidly, and so it's kind of a weird temperature. It's very cold, and the oceans haven't done much yet because we're less than a year, an Earth year into the simulation, and so this is once you run this to equilibrium, the surface temperature pattern will be very different. Could do better color bars. But that's how you check. This is where you would plot your surface air temperature. I mentioned net radiation, so that's here. Could look at your net radiation of the planet, and every variable has the horizontal distribution in lat-lon, and then the Hemis version, which just gives you 3 numbers. So it gives you 3 numbers for I think it's the southern hemisphere first, northern hemisphere, and then the 3rd number is the global mean. All right. So all your AIC, there's a lot of variables in here that you can look at. You can also make sure your topography is sensible. So I showed you the topography file, but just make sure why. Oh no, this is I'm sorry, this is height in meters. There's another one that's ground fraction or something like that. So just make sure your basic things like your incident radiation, your topography is what you think it is. That will avoid a lot of headaches. You don't want to run a simulation for 5 weeks and then realize that you forgot something and your boundary conditions are all wrong. If you do area averages of variables, this AXYP variable is grid cell area. It's basically a cosine latitude dependence essentially, but that's the size of grid cells on a sphere, which increases toward the equator, obviously. So if you average spatially, then you want to weight by AXYP. Not sure. I think so. I am supposed to have like 7 or something more minutes, so I think I could just take some questions. I ran through that quick, but I'll go back to the run deck. And
sure, if people have questions for this, please.
Okay, this is all recorded, so and I'm available on email
as well. I guess you did a great job, Chris. Everybody got 100%.
I guess everybody knows how to run the model now. Great. All right, we're good.
Okay. Well, there's no questions. Then we take a break to the top of the hour, and we'll reconvene, and everybody can ask their questions then. That sounds right. Okay, let's do that. We'll take about a 20-minute break and see you all here for the last hour of Q&A. So anything we've discussed today or even yesterday, you're free to ask questions about, or if you've had enough of us, you can go to sleep or go do something else more interesting. Okay, we'll talk to you all soon.